All right, so it's my great pleasure to be here. Thank you, the organizers, for having me on the program. So now it is my job to entertain this audience with a highly technical paper after lunch. I hope you have had enough coffee. So in fact, I am going to present a watered down version of the paper, and I'm going to leave all the technical details to my discussant or interested readers. All right. So today I'm going to talk about statistical limit of arbitrage. Just to be clear, the arbitrage we're going to talk about is not like pair trading, like you have a stock trade on two different exchanges and things like that. We're going to talk about statistical arbitrage, which is a systematic strategy where investors trade thousands of stocks and they neutralize systematic factors and profit from alphas and subject to risk of idiosyncratic risk. Okay, so that's the kind of strategy we're going to talk about. All right, so this is a joint work with my student Rita, who's now a professor in Indiana, and also my colleague Steph Nagel. Okay, so there has been a surge in the number of papers recently, in the recent 5 years, applying machine learning to asset pricing, right? So in theory, they should make statistical arbitrage investing a lot easier and more lucrative. Right? Recently, Brian and I have posted a survey summarizes all these recent advances. Now, there is a question which is yet to be answered. Is there a ceiling for gains in machine-learned arbitrage, okay, which is a sexier term than statistical arbitrage, but essentially the same thing? Now, this paper, which I'm going to present, will address this particular question. Okay, and our answer is yes. All right, so machine learning is not like something that would give you an infinite Sharpe ratio. We know it's impossible to have that, right? So, but the key message of the paper is that the ceiling is actually much lower than what investors might anticipate. All right, so that's the key point of the paper. And the reason is the pricing errors, okay, like alphas that you see from the market, are not easily translated into arbitrage opportunities. Okay, so in other words, alphas are not equivalent to arbitrage opportunities. Okay, so I'm going to kind of provide you with a model to explain this simple point. All right, so the whole foundation of the paper is on Ross' well-known arbitrage pricing theory. Right, so in APT, Ross can rule out near arbitrage opportunities and based on true parameters in the return generation process. Right? So in Ross's model, arbitragers know exactly what the true parameters are so that they can build mean variance efficient portfolios. And then Ross shows that it's impossible to have an infinite Sharpe ratio, and as a result, you should have some alphas in the end, but alphas cannot be very large. Now, this assumption that arbitragers know the true parameters as in rational expectation asset pricing models is a long tradition of asset pricing following Lucas 1978. All right? But in practice, arbitragers, they must learn about alphas from statistical analysis prior to investment. So typically, rational expectation assumptions are benign because in the limit, right, so when you have enough sample size, you will be able to learn the parameters pretty well. As a result, implications from APT that assume rational expectation should not look very differently from what's going to happen in practice. This is, however, not true. Okay? The reason is in APT, there is an increasing number of assets. All right? And as a result, learning a large number of alphas within a limited time, okay, with a limited sample, pose a significant challenge for statistical arbitragers. And this statistical challenge poses a limit to arbitrage. And this is the key intuition of the paper. All right? So there has been a literature on limits to arbitrage based on, for example, transaction cost, short sellers constraint, financing constraints, and et cetera, right? But statistical limits to arbitrage is something new. It's a new channel that we come up and contribute to this literature. All right, so in terms of statistical arbitrage, I think Nobel laureate Marais-Strauss has a very interesting description of LTCM's arbitrage strategy, right? So basically, these arbitrageurs learn a tiny spread on each of thousands of trades as if it were vacuuming up nickels that others could not see. All right? So what we're going to argue is that maybe in the real world, the challenge in facing arbitrageurs is like this. There are lots of coins on the ground. Many of these coins are fake. Some of these coins actually have negative value. All right? I mean, if you pick it up, you lose $1. Okay? So as a result, it is extremely difficult for arbitrageurs to pick up precisely all these nickels, all these coins. Okay? So that's why, consequently, there must be real coins left over on the market, on the ground. So that's essentially the story we're going to tell. Okay? So keep in mind this picture. So now let me summarize the key theoretical implications of our paper. So first of all, we document these statistical limits to arbitrage in precisely the same model as Ross's APT. Okay? It's a linear asset pricing model. The key distinction is that in our setup, we do not allow arbitrageurs to know the true parameters, the true alphas of stocks. Arbitrageurs, in our world, have to employ a feasible trading strategy. By feasible, I meant that the trading strategy must be dependent on historical data. Okay? They have to learn from historical returns to infer alphas, okay, based on which they can make investment decisions. Now, in this world, we derive the optimal feasible Sharpe ratio for any arbitrage strategy. Okay? There is upper bound, and this upper bound is significantly lower than the infeasible Sharpe ratio in Ross's original APT. Okay, so that's the Sharpe ratio based on observations of true alpha, which in reality never happens. Okay, and we're going to show, so in other words, we establish a theoretical gap between this feasible Sharpe ratio and the infeasible Sharpe ratio. Now, to get back to the main equation that I started, I like to interpret this infeasible Sharpe ratio as a measure of pricing errors. Okay, so how much price error there is. And in fact, it is closely related to the so-called Ross-Shankin test, the GRS test in empirical asset pricing. The feasible Sharpe ratio, on the other hand, is a measure of investment opportunities. Okay, and we show they are not the same. In addition, right, so we have established an upper bound, right? We're going to show you a strategy, we call it an all-weather trading strategy, that will help you achieve this feasible upper bound of Sharpe ratio, all right, without knowing the true parameters in the model. Okay, so this is something that we also contribute. And finally, we're going to examine lots of alternative, commonly used machine learning strategies. We're going to show you that these strategies are optimal only in certain scenarios. They're not uniformly optimal. They could be good for certain scenarios. If in reality you feel like alphas should look like that, then you can find the corresponding machine learning strategy that explore that kind of alpha. But remember, the all-weather strategy we develop does not rely on any assumptions. You can always just use that strategy regardless of the scenarios. All right. So now in terms of empirical findings, we have some illustration with a particular factor model. And the model that we use is very similar to Barra's. Many of you here are using that model. So we're using a 27-factor model, 16 style factors and 11 dummies, right, to explain the cross-section of individual stocks. So when you run the cross-sectional regression, regressing returns next month of individual stocks onto Barra characteristics, you can explain on average about 8% time series cross-sectional variations over time. That means that there's a lot of unexplained variations, cross-sectional variations in the residuals. As a result, learning alpha is truly difficult. Okay? Secondly, we show that among over 10,000 statistics or stocks that we look at, very few of them have alphas. Okay, statistically speaking, all right? So in other words, alphas in reality are very rare and very weak. Okay, you don't have huge t-statistics for individual stocks. And finally, we use our strategies to build this optimal feasible portfolio to explore the Sharpe ratios. And we find there's only, like, roughly speaking, 0.5. Okay, so a modestly low number in terms of the optimal feasible Sharpe ratio. All right, so that means APT works pretty well, right, based on the model that we propose here. So in other words, this is an economic test of APT violations. Very different from the GRS test, which is a statistical test. Now, finally, we show that this 0.5 Sharpe ratio is much lower than what investors might perceive from the market. So in other words, if you estimate the theoretical or infeasible Sharpe ratio in practice, on average, it's like 3.0. But in fact, you can only pocket about 0.5. These numbers do not take into account transaction costs. If you take into account transaction cost, the feasible Sharpe ratio is even lower. All right? So in the end, the empirical evidence point out that the APT works pretty well, at least based on this model that we kind of use. All right. So now let me dive into details. Okay? So I'm going to focus on the reasonably simple model. So if you're interested in more realistic model, you should definitely read our paper. All right? So for now, I'm going to use this toy model, where returns is an n-dimensional vector. There are n stocks that we're trading, and it equals alpha plus ut. Alpha is what we all want. It's an n-dimensional parameter, and ut is idiosyncratic shocks. Okay? And for simplicity of the talk, I'm going to make ut IID normal 0, 1. The reason is volatilities are very easy to learn compared to alphas. So that's why, in theory, it does not matter at all. All right. So now, with perfect knowledge of alpha, in such a simple model, the mean variance optimal portfolio strategy, W, should be simply equal to alpha. All right, so if a stock has more alpha, you allocate more weights to it. And that strategy will earn you a Sharpe ratio square root alpha transpose alpha. All right, so this is essentially classical APT. Now, Ingersoll, in Journal of Finance paper, basically refined the argument of APT and shows that absence of Ross's near arbitrage is equivalent to S star is bounded by some constant. So in other words, APT never says alpha should be equal to 0. APT tells you that alpha is present, but does not give you infinite Sharpe ratio. Okay, so that's essentially the implication from classical APT. However, near arbitrage under knowledge of alpha, or knowing alpha, is not equivalent to near arbitrage without knowledge of alpha. Okay, so let's look at a simple feasible strategy. All right, in this word, okay, arbitragers is not knowing alpha. They have to do not know alpha. They have to estimate alpha. All right, a very simple estimator is take historical returns, take average of historical returns. All right, we call it alpha hat. And by simple math, alpha hat is a noisy signal of the true alpha with some sort of idiosyncratic risk, U bar, left over. Okay? Now, if we use such a strategy, W hat equals alpha hat, what would happen? Well, turns out, by very simple calculations, you will learn that this trading strategy will give you a Sharpe ratio S that has a significant gap to S star, which is the infeasible optimal Sharpe ratio. And this gap depends on 1 over t and n over t S star square. Now, if t is really large and n over t is somehow very small, then there is no gap, right? The ratio is equal to 1. In that word, rational expectation works perfectly. In reality, this is not the case. N in reality is in thousands, right? So t is in reality in hundreds of months, right? So as a result, the ratio could be really large. Okay, to show you that, I'm going to give you a non-trivial example, slightly non-trivial example, very concrete example. It's only an example. So suppose alphas are joined from this IID distribution with rho over 2 probability being mu, and minus rho over 2 probability being minus mu, and 1 over rho probability being 0. Why I like this model? Because in this word, mu and rho characterizes the strength and rareness of alpha, right? The larger mu is, the larger the signal is. The larger rho is, the more alphas you have. So these two parameters perfectly characterize some properties of alpha that I would like to understand. Now, suppose mu is getting smaller and smaller as sample size goes to infinity. And the rho gets smaller and smaller as the cross-section of assets goes to infinity. And suppose square root of n over t goes to infinity. Well, this is just one example. Now, if you look at the infeasible Sharpe ratio and the feasible Sharpe ratio in this economy, you will find out that the infeasible Sharpe ratio goes to infinity. So in other words, if you truly believe Ross's CPT, you should definitely run into this market and trade. However, if you use the infeasible Sharpe, if you use our feasible Sharpe ratio, the Sharpe ratio actually goes to 0. All right, so in other words, you should never go to this market. Okay, you will not be able to benefit from it, profit from it. And the reason is the signal is too low. Mu is 1 over root squared t. It's very low that investors cannot really distinguish that from noise. Right? And the noise of average returns is also at this order. So that's why investors are confused about signal and noise, and then as a result, it's impossible to make profit from here. All right, so these are just examples to demonstrate why classical APT is not sufficient. We need some new concept of APT. Okay? And there are some more difficult questions that we left over on the table. First of all, is it possible that someone smarter can come up with a better strategy that closes this gap? Because so far, we only talk about strategy alpha hat. There is no reason to believe that this is the optimal strategy that one should be using in this economy. Right? So what is the optimal strategy? Okay, so these are questions that in order to fully establish a gap, we definitely have to understand these questions. All right, so here comes the first key results of the paper. Okay, so we show that for any trading strategy W hat, feasible trading strategy, all right, there is an upper bound on its Sharpe ratio, SW hat. So SW hat is bounded by SOPT, okay, with a tiny error that goes to 0, OP1. All right? And this feasible strategy W hat is based on historical data, okay, historical returns. All right, so what is this upper bound? If you read it more carefully, this upper bound, SOPT, is effectively determined by the expected alpha, not by the true alpha. All right, so G here, script G here, is the information set generated by historical returns. Okay, so the best strategy can only achieve the optimal Sharpe ratio using expected alpha, not the unknown, not the unknown alpha parameter. All right, so that is an upper bound. And this upper bound is significantly lower than the infeasible Sharpe ratio that Ross developed before. Okay, so now we actually also provide a solution to a classical problem of mean variance portfolio allocation in the presence of parameter uncertainty. We know that in the case where we know mu and so we know mean and the covariance matrix, we can find mean variance portfolio allocation like being the optimal one very easily, right? So we know the formula. But in the world of uncertainty, we don't know the true parameters. What is the optimal trading strategy? Our paper actually provides a solution to that problem as well. Okay, so for now, I only established an upper bound, okay? So I am going to show you there exists a strategy to achieve it. Before I do that, first of all, I'd like to show you a picture of this feasible Sharpe ratio in this economy, all right? So in this economy, I'm going to show you the feasible Sharpe ratio for many different parameter values. On the x-axis, from left to right, signals becomes lower and lower. On the y-axis, from below to top, alphas become rare and becomes more and more frequent. Okay? So in other words, so if you are looking at the top left corner, that is the scenario where you have lots of alpha, and alphas are very, very strong. And in this case, the optimal Sharpe ratio is like 70 annualized, which is impossible. We never see that in reality. Okay? So on the right-hand side, on the bottom, on the right-hand side, this is where the signal is very weak, and also alphas are very rare. And as a result, the optimal feasible Sharpe ratio is fairly close to 0. Okay, so where we are in reality, probably somewhere in the middle, where we have seen Sharpe ratios, feasible Sharpe ratios that firms have achieved in the order of 1 to 4 to 6 to 7, right? So that's pretty much where we are. All right, so now if we calculate the ratio between feasible and infeasible Sharpe ratios, and we can see that only on the left corner, the ratio, the gap, there's no gap, right? The ratio is like 1.0, okay? So only towards the left end, all right? So there is no gap between infeasible and feasible, which means that rational expectations are relevant. But as soon as you step outside this dark blue area, there is a substantial gap between the two. And in reality, we live in those lighter blue areas, okay, where there is a significant gap between feasible and infeasible Sharpe ratios. And the gap hinges on the sparsity and the strength of alpha. When alphas are large and very, very frequent, then learning is easy. All right? Infeasible Sharpe ratio is getting closer to the feasible one. Feasible one is getting closer to the infeasible one. Otherwise, there is a gap. All right, so now I'm going to discuss what is the optimal strategy here. All right, so the optimal strategy based on this equation, right? We know the upper bound of Sharpe ratio. So clearly, the optimal strategy should depend on the expected alpha. All right, so if the expected alpha is high, you allocate more to that stock. Otherwise, you allocate less. Now, if we know the distribution of these alphas, then this conditional expectation can be easily evaluated using Bayes' rule. All right, so the model is relatively simple, and you can just do it using Bayes' rule. Unfortunately, we do not know the distribution of alpha. Nobody knows, okay? The cross-sectional distribution of alpha. All right, so we have to estimate this conditional expectation. And it turns out there is a well-established statistical literature called empirical Bayes. All right, so using empirical Bayes, we can construct a non-parametric estimator of the density of the posterior distribution of alpha hat, and then based on that, we can build an optimal training strategy, W hat OPT. If you look at this strategy, W hat OPT I, so the weight allocated to the I stock, is equal to alpha hat I, right? So that would be the naive strategy, plus a Bayesian shrinkage term. All right, so in other words, once you have estimated alpha hat, using time series average of returns, you should not directly use it. Okay, you should do some Bayes shrinkage, and that would give you the optimal strategy. All right, that would give you optimal strategy. So in the end, we show that using such a strategy, you can achieve uniformly optimal performance. You can achieve the upper bound that we developed a few slides ago. All right, so now I'm going to discuss some strategies that are very common in practice, strategies that many of you have been using. The first one is just W hat equal to alpha hat, right? The very simple naive strategy. So it turns out this strategy is pretty good. So I'm reporting the ratio between this strategy and optimal feasible Sharpe ratio. All right, so that's the best you can get. It turns out most of these areas on the plots, on the table, these numbers, the ratios are very close to 1.0. All right, so meaning using such a naive strategy is almost optimal. In particular, if you look at the right end, right, the right end of this figure is area where alphas are very, very rare. So in other words, when alphas are rare, do not try to do more statistics to distinguish them. Just use alpha hat. That's good enough, okay? However, if you look at the lighter blue area, so that's where alphas are not rare, and many of them are actually not very large. All right, so that's the area, that's the area where alphas are rare, okay, so because the y-axis is low, but signal strength is very high. So in other words, there are some stocks that have truly alpha, but such stocks are very rare. So in that scenario, you should do more efforts into statistics to truly figure out which stocks have alpha and allocate more weights to that. Right? Without doing anything more, just use alpha hat is actually a terrible training strategy. There is another strategy that has been proposed by well-known researchers in the profession, where they discuss that there is a false discovery rate problem in the alphas. All right, so there are many signals. Okay, so maybe we should be using some fancy statistics to truly figure out which alphas are real alphas, which alphas are not real, and only trade those real alphas. If you use such a strategy, it is only optimal when there are a lot of strong alphas. All right, so if there are lots of strong alphas on the left-hand end, then you should be using such a strategy, and you will be able to kind of benefit from that. But as soon as you deviate from that word, your strategy becomes extremely conservative, and you miss lots of opportunities. Okay? So in other words, false discovery rate control is a statistical criterion. Here, we're talking about investment criteria, Sharpe ratio. These are two different optimization problems. Okay? So if you truly want to benefit from getting a higher Sharpe ratio, you should not use false discovery rate control. All right, let me skip Lasso. So finally, in the next 5 minutes, I'm going to summarize our empirical results. Okay? So the theory basically established a gap between infeasible and feasible. I am going to kind of use some a factor model to kind of show you the gap between these two numbers in practice. So I'm going to use this Barra model. Okay, we replicated ourselves. Okay, so we get like 27 characteristics to describe individual stock returns. This is the time series of the cross-sectional R-square. Regress next month's individual stock return onto these characteristics or descriptors in Barra's word. And you can see this R-square is fairly low. Okay, so they're about 8% on average over time. And this simple model has done a pretty good job. Right, so we have done some earlier work and developed machine learning strategies to kind of look at these R-squares. And the best we can get is about 12 to 14%. And so here we got like 10% using linear model, which is already pretty good. So now once we get rid of these residuals, we're pretty much living, once we get rid of these factor exposures, we're pretty much living in a world where we have a toy model, right? We have alpha, we have the residuals. Now we look at the histogram of the t-statistics of these alphas. You can see that most of these alphas for individual stocks are very rare. Okay, so they do not, there's like very few percent exceeding 2.0 statistics. If you translate into Sharpe ratio scale, fewer of them are greater than 1.0. All right, now this figure is showing you the cumulative returns of 4 different strategies that we studied. All right, so the red one is the optimal strategy that we have actually established, the all-weather strategy. The blue one is cross-sectional regression, the simplest alpha-hat strategy. And the green one is based on the BH procedure to do false discovery rate control. And the orange one is based on Lasso. So the point is not really to show that our strategy is better or worse than these strategies, right? Because some of these strategies are good in certain DGPs, in certain world, right? So the point is really that all these strategies learn a relatively low Sharpe ratio, okay, only 0.5. Now in comparison, if we estimate how much pricing error there is in the economy, in the market, all right, so we can actually estimate that. That will be the blue line on the bottom. Okay, ignore the orange line, I have no time to talk about it. So the blue line on the bottom tells you what is the amount of pricing error you see in this model. And on average, it's about 3.0, all right? So which is much higher than 0.5 that we have actually estimated. So some of you might be confused, like how can you estimate the infeasible Sharpe ratio? What is the intuition for that? Well, think about the coin example that I showed in the beginning, right? It's very hard to distinguish which coin is real, which coin is fake. But I can basically, weight all the coins and figure out how much percentage of the coins are fake, how much percentage of them are actually real. So in other words, estimating the infeasible Sharpe ratio using data is easy. But it is not possible to come up with a strategy to achieve that infeasible Sharpe ratio. All right, so that's kind of the point. All right, so now let me conclude, okay? So I have only 30 minutes, so I basically leave all the technical details in the paper. The paper will take care of all volatility learning, take care of all the other technical details. So we're looking at a factor model instead of a toy model, et cetera. So in the end, we demonstrate a statistical limits to arbitrage. And the economic consequence is that this statistical limit widens the bound in which mispricing can survive in the presence of arbitrageurs. Now, I would also like to comment on that there's a lot of empirical papers, including some of the papers of myself, documents that using machine learning can learn like very good Sharpe ratios, right? But these Sharpe ratios are only lower bounds, okay? Because someone smarter than us can come up with a better machine learning strategy that dominates the numbers that we have produced. To really understand the upper bound, we need a theory. Okay, and the theory provided in this paper basically shows, regardless of what machine learning strategy you want to use, as long as your strategy is feasible, there is a theoretical upper bound that any strategy cannot exceed. All right, so we kind of provide an upper bound. And the gap between this infeasible Sharpe ratio and feasible upper bound, is always going to be there. Okay, so some of you might wonder, hey, you are using a very simple model. The truth is, if you want to make the model more complicated, For example, you can add, covariance matrix estimation, non-sparse covariances. You can add model mystification, many factors. Then rational expectation investors will benefit from that, but statistical arbitrageurs will suffer from that. So the gap will be even larger. All right, thank you very much.
Thank you, Chris, for inviting me to discuss this very interesting paper. I enjoy reading it a lot. Let me maybe first give you a little bit more background before I start. As you all saw in Dacheng's presentation, this is a pretty rich paper, pretty sophisticated paper. I do think this is a very hard paper to discuss. Using Dacheng's language, right? I do think this is kind of infeasible for me to generate much alpha, given how much beta they have already claimed in this space, because most of the authors are leaders in the literature. For those of you who haven't read the book by Stefan, Machine Learning in Asset Pricing, and the survey paper Dacheng also mentioned, I highly recommend you to read those too. I myself learned a lot from the book and the survey, so I do think I really have to, work hard to see something pretty much beyond the territory here. And also to be fully transparent, my show number is 2, in the sense that we share a common co-author, Jianqing Fan, who is also a leader in the literature. So I make sure I will try to be as objective as possible, maybe as tough as possible in discussing this paper. Okay. Given how hard my job is, still, I want to tell you, I immediately say yes when Chris asked me to discuss this paper, because I also thought this is actually an easy paper to discuss. Obviously, it's a fantastic read and also a very polished paper, but as I read the paper, as you saw the paper, I'm pretty sure you're going to quickly identify the 2 keywords of this paper: learning and arbitrage, which is something I've been thinking about for my career. And so when I think about this, I thought maybe what I'm going to do in the next 12 minutes is to give you my understanding, my take of those 2 keywords, to give you maybe my take of the big picture. How can we better put this paper into context? This is obviously a rich paper, sophisticated paper, but I do think there's some room for the authors to better clarify the contribution against the huge literature. And also, I'm going to make some suggestions about potential follow-up work, hopefully, to help us better get the big picture as well. Okay. So first thing I want to talk about is big picture. I do think this is obviously a paper about asset pricing, about arbitrage, but I think fundamentally this is a paper about expectation formation. We care about asset prices, and we do form expectations about asset prices, about returns, and that's how arbitrageurs do arbitrage. So when we think about this, there's really a long, long literature before asset prices thought about beliefs, thought about how we should view asset returns, asset prices, going back to Milton Friedman and Edmund Phipps, talking about the idea of adaptive expectations in the sense that they argue that people are adaptive. And they look at today's inflation, and they think, okay, if inflation is high today, they expect inflation to be high for the next 6 months. And the same idea applies to asset prices, applies to asset returns. If asset prices are high today, they expect asset prices to be high for the next 6 months. Today, some people call that maybe extrapolation or maybe diagnostic expectation, but there's really a long tradition there, which is pretty much the first generation models talking about expectation formation. Before the Lucas critique, which brings the idea of rational expectation into the landscape of macroeconomics and finance. And the idea is, for those of you who have kids, you know how smart they are, right? They're not just being adaptive, but they're smart. They always know where you put the toys, the candies, where you are. They always, do the best guess, and they are almost right. And that's exactly what those people view, households view firms, when they think about beliefs, when they form beliefs about macroeconomic environment, about policy changes, they always get things right. And as you know, Tom Sargent and Robert Barrow, they also push this agenda forward, and that's, I mean, the huge literature today, rational expectations, that's a second generation models talking about formation of expectation, but very quickly people realize people do deviate from that benchmark. That's a benchmark, that's a useful benchmark, but people do deviate in the sense that it's not like people make mistakes. We're smart in the sense that sometimes we just look at, for example, our checking accounts, not every day, right? So maybe you look at that every month. You look at your brokerage account every month. So that's a notion going back to Mankiw and Ray's rational inattentiveness. And then Chris Sims introduced the idea of rational attention. Still, you look at your bank account, you look at your stock brokerage account every day, but you pay more attention some day and you pay less attention some days. And also, Stefan Eckley has another paper with Uraiki Momandile talking about learning from experience. It's like, what comes to your mind first will be put on more weight when you think about expectations. Think about this. Right? They don't mean that people make mistakes, but that means that people rationally, selectively pay attention to something and they pay less attention to something else. And that's exactly, I mean, I want to mention this. This is like the third generation of models about belief formulation because I really want to put this paper into the context. When we think about this paper, I do think it proposes a new agenda, pretty promising agenda, thinking about how smart people, sophisticated people, form expectations in terms of thinking about arbitrage. And I think it's also useful to bring another paper by Ian Martin and Stefan Nagel to the picture, in which they also talk about statistical learning under big data, right? I mean, we think about this, right? Remember, the idea is people selectively pay attention to something. They selectively pay less attention to something else. Here we are talking about a high-dimensional inference problem because of the introduction of big data, right? You know, today, I mean, compared to what used to be 3 decades ago, 2 decades ago, we have a lot of different dimensions to take care of, but simply, we can't pay so much attention to so much things. And that's the idea. Investors never know perfectly. In Martin and Nagel, they care about cash flows, but they never learn cash flows perfectly. So that means that at the cross-section, when you think about, I mean, typically cross-section as a pricing models, that's going to lead to in-sample, but not out-of-sample predictability. That means that when we have predictability in the data, it doesn't necessarily suggest risk premium. It might be a reflection of people's learning persistence. It might be a reflection of this big data problem. And the same idea goes to this paper Dacheng just present. When you think about arbitrageurs, they learn about model parameters. They never know the true parameters of the model, and they face a high-dimensional inference problem. And that's going to lead to the upper bound. This is really, I mean, I do think this is a big deal to literature. Why is this a big deal? Because when you think about the recent literature about applying machine learning method to asset pricing, typically people come up with some strategies, some portfolios based on machine learning techniques, but those are really lower bound. Lower bound meaning, I mean, if you follow the strategy, if you follow the portfolio, you can do something. But it doesn't necessarily suggest that there is a limit to arbitrage. Limit to arbitrage, if you really want to talk about that concept, you need to theoretically establish a concept of upper bound. And that's exactly something Dacheng also mentioned. I would love to encourage authors to highlight this concept more, to link it to the concept of limit to arbitrage, and also maybe highlight your contribution more in the context of expectation formulation. You do have everything, but this is probably something I would do to really highlight the big picture. Let me make 2 suggestions in this direction of thinking about big picture, thinking about arbitrage across different literatures. Also, maybe for those of you who are in the wrong, who do asset pricing arbitrage at frontline. There is a notion called econometric learning. What's that? Remember, so a key contribution of this paper is learning persistence. And this persistence stems from a high-dimensional inference problem. And when you think about learning, so that's, again, so don't get me wrong. I'm not saying, I mean, this is something already in the literature, but the macro literature has talked about learning for a long time. And they come up with the idea of so-called econometric learning, arguing that when households, when firms make forecasts about macroeconomic variables, they do the same thing. They think of themselves as econometricians using available data up until today to make inferences about what could happen going forward. So that's exactly the same idea. But there's a key difference between that literature and today's paper, which is the old literature typically considers a low-dimensional inference environment. This is not surprising, right? Because when you think about what happened again 3 decades ago, I mean, there are just so many macroeconomic variables we should care about, like interest rate, like exchange rate, or maybe 10-year T-bond rate. So that literature typically focuses on conditions under which convergence to rational expectations happens, and that's what we call learnability. When that happens, that means that as econometrician, we can still view rational expectation as a good benchmark. But there is really an exception. I would encourage authors to look at this paper by Evans and Hankabaja, 2003, Review of Economic Studies. They formulate the idea of constant game econometric learning. Where's the goal of, again, so we think about this, right? So the huge literature talks about when learnability happens. So, it's when the learning equilibrium converges to rational expectation. But those authors argue that we can also use persistent macroeconomic fluctuations as a reflection of people's learning problem. Learning may not be perfect, and we can look at that. We can use that to better understand why macroeconomic fluctuations are persistent, because that's not something which would have happened in an otherwise REE framework. And inclusion, I mean, for that, right? So constant gain econometric learning, it's like you build a metric model, and you put higher weight on recent innovation of economic variables. So this captures the idea of people, again, so they pay more attention to recent events, and maybe recent events come to people's mind more easily. An important prediction of this model is they're going to generate a predictability of unconditional macro moments like interest rate, like exchange rate, and that's pretty much analogous to Ian Martin and Stefan Nagiel's earlier GFE paper. So that's exactly something I would encourage you to look at. Maybe you can push your agenda to this literature. There could be some pretty interesting. Still, they are economically deep, but maybe you can easily look at optimal monetary policy design on the big data, right? So this is not something, just as an intellectual exercise, because it's becoming more relevant today. When you think about those firms, right, when they form forecasts about macroeconomic conditions, right now they increasingly use satellite data, digital footprints. They have a lot of apps, right? They're collecting data about ourselves, and they use satellite data to look at a lot of different things. It's a high-dimensional inference problem, and if firms are doing that, how should a central bank think about the optimal design of monetary policy or fiscal policy? This is exactly something you can use your framework to better understand. So I would encourage you to think about that. My second point, suggestion, and also my last suggestion, quantifying the difficulty of learning. This is actually something Dacheng already mentioned, but I would love to push you a little bit more on this front. The wedge approach. What do I mean here? Again, so one big contribution of this paper is the establishment of an upper bound of Sharpe ratio. Again, so that's a big deal, right, compared to the literature, which typically focuses on the lower bound, and this is suggestive of limited arbitrage. And what's nice about this paper is it's not just a theoretical exercise. They can do both. They first construct SOPT, which is the feasible upper bound, and they can propose a portfolio which is going to achieve this upper bound. So that means that this upper bound is very tight, but that also means that data-wise, we can exactly get the number for SOPT. And also, section 6.2.6 estimates the infeasible optimal Sharpe ratio. And that means you can come up with two numbers, and you can exactly look at difference. That's important. Actually, Dacheng already mentioned the idea. There is a concept called wedge. I want to mention a couple of papers in the economics literature talking about how people can use wedge to formally measure frictions, to measure the deviation of a realistic friction of the economy, and how large a deviation is from a frictionless, complete market economy. So I don't have time to talk about details, but the basic idea is you can look at, wedge. You can look at wage, people's wage. You can look at exchange rate. You can look at prices. And if you look at two different markets, and you compare the price, you compare the wage, you compare the exchange market, so that's going to give you a sense of economically how large the frictions are for one economy compared to the other. So this is something important, because I'm pretty much sure you can look at the literature and you can use this idea to formalize relationship between those wedges and learning frictions in your environment. Because what you fundamentally care about is how hard It's a slotting problem. And there are other frictions, right? There are other limits to arbitrage, the leverage constraints, the short selling constraints. And maybe you can even do a decomposition of that. And I think there's pretty much room for you to explore in that direction. Let me conclude. This is a very beautiful paper, important paper on statistical limit of arbitrage. It's a rich paper, so instead of making a lot of detailed comments, what I do here is to hopefully help us to better understand the big picture, upper bound. So that's really a big deal, and there's no agenda. I didn't make two suggestions, but I think there's just examples. I would love to leave the creative license to the authors, and I do think this is something pretty exciting for all of us for the next decade or even going forward. Thank you.
Right, so I think I'm just going to say, Yao has done an excellent job. I really appreciate his insight. And to extend this framework to other settings in economics in general is something that we're thinking about. Maybe there's one more thing that I'd like to kind of clarify or emphasize a bit more, right? So if you think about the learning difficulty arising in this model, if you think about it, our model is based on the masterpiece of APT, with only one restriction that arbitrageurs have to use feasible trading strategies. And then the rest just follows, right? So in other words, we show a limit that will not disappear asymptotically. If you look at the learning literature, most of the learning is about a low dimensional parameter, and the learning effect will disappear asymptotically as the sample size goes larger and larger. This is one important distinction. Secondly, we do not put any restrictions on economic agents' strategies, right? So some of these papers that are discussed in the literature, they kind of impose all kinds of restrictions so that they can develop, some solutions, right? So here we ask economic agents or arbitrageurs to do whatever they can, try their best, and we show there is a gap between the two. So these are kind of two important distinctions from the learning literature. And thank you very much.
I do have a question. So crises sometimes happen that are surprises based on analysis of past statistical data and kind of wipe out a strategy. We saw the quant meltdown in August of 2007 would be an example of this. Related to that is the idea that some strategies that appear from a statistical perspective to be profitable are actually sort of like writing out of the money options after a time period when they never would have expired in the money. And so your statistical model says they're not going to expire in the money, and then they do. And when that happens, strategies, which in your case would correspond to the individual assets that historically have very low correlation, all of a sudden become very highly correlated, like we saw in the LTCM crisis. So my question is, how does your methodology for coming up with a hypothetical optimal strategy for calculating a conditional expectation work when you don't know the distribution, and these bad things can happen, like options that you've never seen expire out of the money, in the money, suddenly expiring out of the money, and everything becoming perfectly correlated that's been orthogonal in the past?
So thank you so much for the excellent question, right? So, how do we take care of these things, like crises that suddenly happened, or correlations that suddenly rise among individual stocks? So, unfortunately, when you develop a model, when you develop a theory, you have to rely on a reasonably stylized model, right? So, for example, your model as well. So, as a result, we will not be able to provide, insight or kind of conclusions in scenarios that are outside the model we develop. Okay, but we can still try to understand what's going to happen in such a way, right? So if there is a crisis, we have epsilons. Okay, we have epsilons that can capture these things, and it will show up in our, risk, and Sharpe ratio will be lower when we evaluate empirically. And if correlations are time varying, then certainly our current empirical evaluations do not take that into account. But the point that there is a huge gap between infeasible and feasible states, right? So suppose there is a crisis and the rational expectation agents would know it, and then they would have a very high Sharpe ratio, but statistical agents would not be able to predict well, and there will be much lower Sharpe ratio, so the gap will stay. So I guess my answer to your question is there's a lot of things that we are kind of outside of our model, and that's kind of what we can do, but the gap stays. Okay, so the gap between the infeasible and feasible stays.
Thank you. Larry? So Pete's question is a special case or a special example of my question, which is more general. My understanding of the result, and this is just my first exposure to it, is that the result comes from the fact that as we increase the number of securities, our uncertainty in the alphas is increasing in a linear way because the alphas are IID. And so I want to emphasis on independence. But in practice, people make correlated mistakes. And so we're talking basically of pricing problems. And so as we get more securities with people making sort of similar mistakes, they learn more about those mistakes. And while your result undoubtedly obtains, it's possible that the Sharpe ratio, this optimal one, could be much higher in an environment where the mistakes are correlated across the securities. And in fact, it may approach the theoretical Sharpe ratio if we don't have, if much of the noise about the alphas is eliminated through growth in the cross section. In particular, if the noise can be eliminated that way. So this is a special case of what, a general characterization of the special case that Pete mentioned, which is, we said, what if everything's correlated? Everybody makes the same mistakes. And so the question is, might things be actually a little better than it seems because of this assumption that each security, the introduction of each security introduces more information, and that increased information is what's damning us.
All right, so thank you so much for the excellent question. So let me mention one thing which I don't quite disagree with you, and there's another thing that I think we can sort of handle, okay? So when we're talking about idiosyncratic risk here, right? Economic agents, arbitrage, are learning alpha and subject to idiosyncratic risk. So I thought you were talking about, sometimes all these idiosyncratic risk becomes highly correlated. And that would be a scenario where arbitrageurs will not be able to fully diversify this idiosyncratic risk. And this idiosyncratic risk will more like a factor, and as a result, the Sharpe ratio will be lower instead of higher. But what would happen, how do we model alphas that are not like IID, right? So can we think about alphas as a function of certain characteristics? This is certainly something that industry people are always doing, right? So you're kind of, instead of estimating alpha for individual stocks using time series average, you're predicting alphas using some kind of secret variables that you hope. And that is something we can totally do, okay? I just have no time to talk about it, right? So basically, you can kind of, write alpha as a function of characteristics, and write your risk model also as a function of characteristics, and do a projection onto the characteristics, and you ended up getting something that is very similar to the model that we have. So the short answer is we can certainly handle some kind of time series alphas, alphas explained by characteristics, and of course, there's limitation of how much we can achieve.
Very, very interesting paper, Dacheng. So you claim your result is like a test of APT of Steve Ross. Yeah. But I'm thinking the key idea of Steve Ross APT, the key idea of Steve Ross APT is like diversification, right? So if you have a little bit diversification, so you can hold like a diverse like a portfolio to kill all the idiosyncratic risk. And even there's like a little bit alpha, you can have like a huge Sharpe ratio. But your paper, I think, is not test on this to be rigorous, right? To be precise. I think you provide some like a complementary channel to kind of select, there's no difficulty or hurdle for investors to take advantage of alpha, construct really high Sharpe ratio. So formally speaking, to be precise, I don't think that's a test for Steve Ross APT. Instead, but you show the result exists. The APT result, but from different channel. So that's my comment.
So I'm very glad that you mentioned this, and please allow me to kind of discuss this kind of literature on testing APT a bit more to address your question, right? So as we have shown you, APT only says you cannot learn infinite alpha. That's it, okay? Alpha can be there, but it cannot be infinite. That's what APT can imply. In the literature of asset pricing in earlier days, many of the researchers are testing a null hypothesis that all alphas are precisely equal to 0. Okay, so in that regard, the GRS test is part of that, right? It's contribute to that literature, testing whether alpha is equal to 0. Technically speaking, no one has tested APT before, because APT says alpha it could be there, but you're testing a different null hypothesis. So what we propose that we believe is an economic test of APT. So I never develop any p-values or things like that. I just build a trading strategy that see how much you can get out of the alphas. If you believe the alphas is large, okay, so then you basically have a rejection of APT. If you believe alphas are small, then you kind of fail to reject APT. So that's all what we can do. But to be clear, there's never any p-values, things like that we develop in this paper.
So I was very curious about the fact that you set the weights equal to the alphas. And I suspect that you're assuming that the alphas are independent of each other. And I can assure you that is almost certainly not true. Do you want to comment on that?
Right, so there are multiple assumptions that we made in the talk, but not in the paper. Okay, so first of all, weights, the optimal weights is sigma inverse times alpha. Okay, so covariance matrix is completely gone from the talk because it's easy to learn. But we do make an assumption that alphas are ID, okay, which is, you're right, that we do make this assumption that alphas are ID, and so that we can learn about them. And I kind of also mentioned that we can totally extend it to cases where alphas are functions of characteristics. Okay, so that would make alpha completely not ID. We just have no time to kind of discuss the results based on that. Okay, so the short answer is we do have extensions to address situations where alphas are not ID, functions of characteristics.
So in the setting where firms differ in their characteristics in that extension, is the idea that like n, the number of characteristics also grows over time, or does the learning problem still persist even if the characteristics either is bounded or shrinks as a fraction of t over time? Or does it have to be that characteristics also increase in complexity over time to keep this from becoming a learnable problem?
All right, thank you so much for the great question. So the way to understand that scenario, like when we have characteristics to explain alpha and beta, the first step is to project individual stock returns on characteristics. And then you are essentially dealing with characteristic sorted portfolios, right? So then we need an assumption that there is a large number of such portfolios. So that's the only assumption we need. So basically you have an increasing number of characteristics.